Good day, and thank you for joining us on our sixth webinar of the series Integrating Dynamic Modeling and Simulation into Your Courses. In this series, we feature experienced professors from various fields who share their insights in incorporating dynamic modeling and simulation into their coursework. The goal of this series is to provide a starting point and direction to help implement these techniques into your own teachings. Today's webinar is presented by Dr. Diana Fisher and focuses around introducing dynamic modeling into high school math courses. Now, allow me to introduce today's speaker. Dr. Diana Fisher has over 20 years of teaching experience with system dynamics at both the high school and university levels. She has authored several textbooks, including our best-selling book, Modeling Dynamic Systems, Lessons for a First Course. She's offered online system dynamics modeling courses for mathematics and science instructors, and she has been an outstanding advocate for introducing system dynamics into more curriculums, and we're delighted to have her today.
Welcome. My name is Diana Fisher. I have infused system dynamics modeling into my algebra, pre-calculus, and calculus classes for 20 years. I have been asked to share the strategy I used to infuse system dynamics modeling into my mathematics courses. As a strategy for infusing system dynamics modeling in a course, the System Dynamics Society pre-college leadership team, of which I am a member, recommends finding those dynamic concepts in one's curriculum that students tend to have difficulty understanding, and having students build system dynamics modeling diagrams or simulations as part of a new strategy to strengthen their understanding of these concepts. Research indicates that understanding the concept of a function is difficult for most students, including those in calculus, and that mapping diagrams can provide a richer foundation for exploring functions. For decades, the approach to learning about functions in secondary school mathematics was to have students practice working with or recognizing functions in 4 different settings: graphically, numerically, from a text description of a function scenario, and symbolically. When I taught algebra in my final 20 years of teaching secondary school mathematics, I added an additional setting: diagrammatically. I would start the study of linear and quadratic functions using the motion detector. A motion detector is a device that sends out a sonar pulse that bounces off an object in front of it and measures the distance the object is from the detector. The purpose was to use an activity that students had some intuition about and make a strong connection between the relationship between position of the student from the motion detector and the velocity the person was moving at, kinesthetically and graphically. So the student is instructed to move away from the detector at a slow, steady, constant pace. The detector, connected to a computer, graphs the position of the student over time and reinforces that the graph is straight because the movement of the student is occurring at a constant pace. The student is asked to repeat the exercise but move away this time at a quick, steady, constant pace. They see that the graph is still straight because the movement is constant, but the line is steeper, capturing that the pace was quick. So tilt connects to the speed of movement. So what we want to do is make a connection between the graph of position and the graph of velocity. Since the pace is steady, the velocity must be the same all the time. Hence, its graph is a horizontal line. But where do we put that horizontal line on the velocity scale? We refer to the physical activity and ask how the different velocity was demonstrated in the graphs of slow versus quick, steady walking. It was demonstrated in the tilt of the line, which students know is called slope. And slope is the position of the position graph is positive, so the horizontal velocity graph must be in the positive part of the velocity axis. Next, we look at a table of data and view the change in the function value, position, for each increment in time, and notice that the change in position is again constant for a steady, constant pace movement. Next, the stock flow diagram that represents this linear function is introduced, and students actually build their first linear model. This gives students the practice to learn how to use the system dynamics modeling software. Stella is the preferred system dynamics modeling software for almost all K-12 schools, not only because it is elegant in its design, but because it is now also free for all K-12 schools globally. Traditionally, these are the different types of functions studied in a second-year algebra course at the secondary school level. When students gain facility building and analyzing stock flow models, the curriculum can now include the function types that are shown here in purple, because the stock flow diagrams make these function types more intuitive for students. While you may wonder how you can add additional topics to your curriculum, remember, these are story problems brought to life. This is the reason students are learning mathematics, to apply mathematical reasoning to understand the world. So I was always able to identify parts of my curriculum I was willing to delete to be able to bring in these stories. Moreover, mathematics will be changing more quickly with the continued availability of technology and the impact that artificial intelligence will have on what should be taught. Certainly, symbolic manipulation practice will take a back seat, though not no seat, to mathematizing and analyzing more types of real-world problems, which will help students better understand their surroundings and be more competitive in the workforce. In mathematics education, we already recognize the need to understand functions from several viewpoints. Closed-form equation representation is very abstract for most students. Providing a diagramming representation eases some of that cognitive load. Moreover, the diagram labels help students gain a more complete picture of the components of the problem. And moving between the equation and diagram representation when dealing only with a single function reinforces the meaning of the parameters and variables in the equations. Notice also that the diagrams tend to connect more closely with the real-world counterparts that we are trying to capture. Consider, for example, representing the behavior of the position of a mass bouncing on the end of a spring. On the left, we see the closed-form equation that captures the oscillation, but the numbers mean very little to the students. Yet on the right, the entire diagram structure captures the essence of the scenario, how the parts are connected, and which parts represent each component. The diagram provides a more visual representation of the system. Why wouldn't we want to help students understand this problem in a form that is as easy as possible to understand? They will always have access to the technological tools to use this representation. Now, for another reason system dynamics modeling is so useful. We can bring more realistic problems into our classroom for students to study. Consider a scenario involving administering medicine to a patient. The only prerequisites for studying this problem is that the students need to have built linear and exponential models. That means this problem could be used in a middle school algebra class. My students have always loved these medicine models. Here is the description of the first medicine model. You are a medical resident working in the emergency room, and a patient comes in who needs immediate medical attention. From your analysis, you decide to connect this patient to an IV drip that will supply 1 milligram of therapeutic drug per minute. This person, you estimate, will metabolize the drug at about 0.55% per minute. What is the pattern of the drug level in the body over 24 hours? With the whole class, we follow this procedure to analyze the task. What is the focus variable? That is, what do we want to track? The drug level in the body. Is there an inflow? Yes, drug is entering the body. What is the pattern of the inflow? Constant inflow because it is an IV drip. Is there an outflow? Yes, drug is leaving the body. What is the pattern of the outflow? Exponential. Drug is eliminating as a percent of the current drug amount in the body. As we progress through the questions on the previous slide, we have built this model on the board. Then I ask my students what the graph of the stock value would look like. None of my students know the answer because they have never had a problem that involves a combination of functions. So I ask some students to come to the board and draw some predicted graphs. I next mention that most medicines must be kept within a therapeutic range to be effective. So I add 2 additional converters on the board, one for therapeutic minimum and one for therapeutic maximum. And I add 2 horizontal lines on the graph pad on the board. Then I tell the students to build this model on their laptops. When they run the model, they get this graphical behavior for the stock, and I ask them why this graph would make sense. Finally, I throw a wrench into the scenario. About 8 hours into the patient's stay in the hospital, one of his kidneys fails. What would happen to the drug level in the body? They don't usually have a quick response, so I ask them what part of the model would have to be changed. They can usually come up with the fact that the decay fraction is smaller and maybe it's half of what it was before the kidney failed. So if the decay fraction is smaller, the outflow is smaller, so what happens to the drug level in the body? Well, it increases above the therapeutic maximum. So what does the doctor tell the nurse to do to fix the problem? There are multiple correct answers, but maybe some answers are better than others, and the answers are discussed. I will skip to the third medication model, taking pills. It is a busy night in the emergency room. A third patient arrives, and you decide to give this patient 2 pills of 375 milligrams each of a therapeutic drug and tell them to continue taking 2 more pills every 4 hours. This person you estimate will absorb the drug from the stomach to the bloodstream at about 4.5% per minute and metabolize the drug at about 0.55% per minute. What is the pattern of the drug level in the body over 24 hours? We go through the question and answer scenario again and end up building this model on the board. I don't have time to explain the graphs, but the students understand the green graph pretty easily and have trouble coming up with the purple graph, so I explain that one. Then they try different scenarios on the model. The fourth model scenario is the study of blood alcohol concentration. In the beginning structure, it is very much like the pill model because the alcohol enters the stomach and is then absorbed into the bloodstream. The additional part of the model is built using questions and answers with the students as a class. This model is already on the student computers and they just experiment with the model. The left graph shows the blood alcohol concentration for a 150-pound male sipping 6 12-ounce beers over 2 hours. I set up the grid so that the lower horizontal line here is at 0.08% and represents the legal driving limit for blood alcohol concentration in Oregon. This shows how long the person has to wait after he quits drinking before he could drive. The graph on the right compares the blood alcohol concentration for a male, the blue graph, and a female, the red graph, of the same weight drinking the same amount of beer over 2 hours. The previous model can be used to show different blood alcohol concentrations based on body weight, gender, type of alcohol consumed, and different types of drinkers. An important core concept in system dynamics modeling is called understanding bathtub dynamics. If you want the level of water in a bathtub, where the drain does not have a stopper in it, to increase faster, most people would say turn up the flow of water from the faucet. But another choice would be to reduce the rate that the water is being pumped out. Well, that is pretty basic, so let's make the problem a little more sophisticated. Suppose the substance measured in the tub is the amount of CO2 in the atmosphere. The inflow, human CO2 emissions, increases the CO2 in the atmosphere. The CO2 in the atmosphere is reduced by natural CO2 sinks in nature, trees, oceans, etc. If we want to reduce the amount of CO2 in the atmosphere, most people would say we need to reduce human emissions, which is true, but that is incomplete. We need to reduce human emissions to a level lower than nature's sinks can remove CO2 in the atmosphere. Moreover, we continue to interfere with nature's CO2 sinks, reducing their effectiveness, so our needed emission reduction grows even larger because the difference between the inflow and the outflow is growing larger, not smaller, over time. That is why it is so complicated to address. A natural topic in mathematics classes is the study of population. Let's see what students could learn by analyzing a basic population model, as is shown in this diagram. An inflow called births is calculated as a fractional percent of the current population. An outflow called deaths is calculated as a fractional percent of the current population. One thing that a math teacher could do is introduce the two types of feedback present in this diagram. I didn't do that in my math classes, and I think that was unfortunate because introducing feedback analysis in math automatically connects math to biology and environmental science, where feedback analysis is a core part of the curriculum, not negating the importance of this topic in understanding almost everything around us. Another use of the basic population model is that I did use in class was to ask students what 3 graphical behaviors this population could display over time. Students don't have trouble coming up with these 3 behaviors. Then I ask them what numeric relationships in the model have to occur to produce each graph. I tell the students that the flows are formulas that you cannot change, and the starting value of the stock cannot change. By elimination, they can tell me that the values placed in the birth fraction and the normal death fraction have to be related as shown in these mathematical statements. Then, if you chose to talk about feedback previously, you can introduce the idea of feedback dominance. Let's consider a deer population in a forest environment. We start again with a basic population structure. We will assume that the birth fraction is larger than the normal death fraction, so this population is growing exponentially. Of course, a population cannot grow exponentially forever. Eventually, resources become limited, placing a constraint on the growth rate of the deer. The multiple limiting factors are collected into a concept called carrying capacity. We hypothesize that as the deer population grows, the constraints in the environment will cause more deer to die due to a lack of food, potential additional weakness from disease, possible additional predation, though a predator is not included in this model structure right now. so deaths have to increase over time. In order to cause deaths to increase in a reasonable fashion, the model has to know how close the current population is to the carrying capacity. So we add an additional converter that I have called effect of carrying capacity on death fraction. This is a special type of converter. Notice the tilde shape within the circle for the converter. That means this converter is defined not with a number, not with a formula, but with a graph. It is a graphical converter. We want this graphical converter to compare the current deer population to the carrying capacity. So we have to connect the stock deer population to the effect converter and connect the carrying capacity to the effect converter. Now we have to define the graph we will use inside the converter. There are quite a few different choices for graphical shapes built into the Stella software that could be used for this graph. When I started learning about system dynamics, I usually used just straight line graphs. So let me take you through the thinking in defining this graph. First, the horizontal axis should always be defined as a ratio, often comparing a stock value, the numerator, with a fixed value in the denominator. In this case, the denominator is the carrying capacity. This ratio can have a smallest value of 0, no deer are present in the environment, or a largest value, for simplicity's sake, of 1. The deer will not exceed the carrying capacity. For the vertical scale, when there are no deer, the death fraction will not change. But as the deer population grows compared to the carrying capacity, we think the death fraction will grow to a maximum of 3 times the normal death fraction. So for each increase in the ratio of deer to carrying capacity, the death fraction will grow a little larger. The vertical value on this graph is a number between 1 and 3, and we will have that value multiply by the normal death fraction to create a new death fraction that the model will use. I'll show you how to do that connection soon. I don't often use straight line graphs in these definitions anymore, but decided to do it this time because it made the mathematics I want to show you in a few slides easier. So the graphical converter has been designed at this point. Notice now a new converter has been added, actual death fraction. This is the death fraction that will be used to calculate deaths in the death flow. This value is calculated as the product of the normal death fraction times the y value in the graph that is sent out to this out of the graphical converter that is growing larger as the population is growing larger, hence increasing the actual death fraction over time. I have placed some values in each converter to use for future reference and for producing a graph when we execute the model. Notice the birth fraction is larger than the normal death fraction. The asterisks mean that the two components feeding into that icon are being multiplied within the icon. This slide I created for my own information. As a math teacher, I want any new instructional strategy I use to have output that is consistent with the output produced by traditional methods. So I placed a few additional icons in this model for my own testing purposes. The first converter contains the closed form equation for logistic behavior that is often taught in pre-calculus. I also created a simple additional stock flow structure that uses differential equations and initial value approach that is often used in calculus for this type of problem. As you can see in this slide, the stock flow model, the closed form logistic equation, and the calculus initial value problem scenario all produce the same output. I can bring this carrying capacity concept into my second year algebra class because I have access to stock flow modeling. If you were to ask students to use system dynamics concepts to explain why the graph is shaped the way it is, they could explain that the inflow is greater than the outflow for most of the simulation since the population graph is increasing. Then toward the end of the simulation, the inflow, births, equals the outflow, deaths. This is bathtub dynamics. Moreover, the shape of the graph at the beginning shows exponential increase, indicating that reinforcing feedback, population and birth, is dominant. The two balancing feedbacks are growing stronger during the simulation until after the inflection point, the sum of both balancing loops dominate the behavior, eventually bringing the system to a steady state. This population behavior demonstrates a transfer of loop dominance. Before I continue, I want to explain why I went through the explanation in detail for the deer with carrying capacity model with you. This is the process I use when I design a system dynamics mathematics lesson for my students. I always build the model first so I know it works. Then I write the story that will lead my students through the thinking they need to be exposed to as they build the model piece by piece. I put questions throughout the lesson to make sure they are thinking about what they are doing, especially predicting model behavior before executing the model. This is the process I use to teach students how to build more sophisticated models. George Richardson, a well-known system dynamicist, has his students copy well-designed models when they are beginners. I did not know George when I started using system dynamics in my classes, so this guided model building story method worked well for me, and I stuck with it. After students practice building linear, quadratic, and exponential function models, they build the 4 drug models. Then they build a population model with a fixed carrying capacity, demonstrating an application of S-shaped growth behavior, and either a population model with a non-renewable resource, demonstrating overshoot and collapse behavior, or a global population and global wheat harvest situation, also potentially overshoot and collapse. They build a determining the time of death model, demonstrating convergent behavior. Finally, they build models involving applications of sinusoidal behavior to study a mass bouncing on the end of a spring model, a swing pendulum model, and predator-prey interaction. These model exercises are spread out over the 9 months of the year. When starting out, I only included a few models in the curriculum and added more over time. It is important to eventually use model building exercises throughout the year so students see this approach as an important part of what they are to learn in the course and not as just a quick 2-week project that they will forget about also quickly. There are other functions, mathematical concepts, and system scenarios that could be added to your course if desired, as identified at the bottom of this slide. The fact that almost all of the interpretations of model behavior is done graphically gives math students much needed extra practice analyzing graphs. Also, since the flow graphs are often analyzed to explain the behavior of stock graphs, this correlation analysis is a very important skill for understanding core concepts in calculus. Since so much of a student's mental model about the structure of a problem being diagrammed and modeled is visual, the structure of the diagram can highlight student misconceptions, so teachers can help students move toward more correct structures. Analysis of model behavior helps students realize they have made mistakes in their diagrams. Of major value is the fact that system dynamics modeling can allow students to analyze problems that would have been out of their reach using closed-form equations. Students never complain to me about doing this type of modeling. This is a predator-prey model. This is a non-renewable resource model. This quotation captures a significant reason to include system dynamics modeling in the teaching of mathematics. It truly expands the world students can experience in mathematics. I will quickly show you one example that I think is a very useful application of system dynamics modeling in a calculus class. Consider the traditional spread of an epidemic model studied via differential equations in calculus. S stands for the susceptible population, I for the infected population, and R for the recovered population. Initial values are given for each population. Also, the differential equations for how each population changes over time is provided. Since the system dynamics software is built on an engine that uses numerical methods to solve differential equations, it is a natural application to translate simple differential equations to stock flow diagrams. Each population would be represented by a stock. These are the three stocks. The differential equations tell us that the S stock has only an outflow, the negative here. The I stock has an inflow and an outflow, and the R stock has only an inflow. So we add these flows. Now we can add the converters by looking at the other variables and parameters in the differential equations. We connect these converters to the flows as shown in the differential equations. Note, I identified the flows with the two differential equations that influence that flow. It is not supposed to represent a product. It is just supposed to represent that the differential equation for the susceptible population and the differential equation for the infected population are both involved in the definition here, and similarly the infected population differential equation and the recovering population differential equation are both involved in defining that flow. There has to be some conversation about the actual problem and how we can rename the single variable letters in phrases that are more descriptive. Notice that I keep the variable or parameter letter as part of the new naming process. Another focus is to highlight the feedback more explicitly in the problem. This stock flow diagram is a possible result of that process. This slide just shows the graphical output of the three stocks in the previous stock flow model. Now we can enhance the story problem by suggesting that the recovered population does not remain immune to the disease. We modify the stock flow model to capture this situation. When I asked my students to recreate the differential equations that would be appropriate for this new scenario, it is important that they see the relationship, and in that matter, I believe the students come to understand the structure of the differential equation better. Although artificial intelligence was not around when I was teaching high school mathematics, I am excited about how this technology can help teachers enhance their teaching strategies. One experiment I did using artificial intelligence was to ask how I might set up a sequence of activities in my second-year algebra class to teach a short unit on the spread of an epidemic. I show the prompt I gave to the free version of ChatGPT 4.0 and the results that AI gave back to me. ChatGPT gave me 7 lesson ideas that included the objective for the lesson, a description of the activity, and some questions, discussion questions to use with the students during the activity. I am showing you only the first and the last lesson description and a description of a possible project students could be assigned. As always, it's important to analyze what AI gives you to make sure it is reasonable with one's expectation for what works best in the classroom. The AI can also give you potential answers to the discussion questions, more detail about the activities, a different set of activities or shorter set of lessons for students who are at a different ability level in the class, and create possible worksheets for students. Another very useful application of AI is the design of new types of assessment questions that would more naturally assess system dynamics concepts that you are adding to your lessons. Here is the prompt that I gave ChatGPT 4.0 that asks it to come up with 2 short paragraphs explaining a problem, one of which is a systems problem and the other that is not. System dynamics is designed to work on systems problems, so students need to be able to identify problems that have systems features, elements, interconnections, and purpose. This is the example that the AI gave me. I will not read it to you, but since this presentation is recorded, you can watch the recording later and read the details that the AI produced. I always ask the AI to give me what it thinks are the correct answers, just to check it and myself. I have not shown that reasoning part of the AI response here. This is another sample question where I describe a brief systems problem and ask ChatGPT 4.0 to list 10 variables that might belong in a stock flow model we might want to create for this problem. Then I told the AI to ask the students to identify the variables that should be designated as stocks and which should be designated as flows. In the AI response, it gave too much information in the directions, so I decided to eliminate part of what it recommended. Although I have not talked about the year-long high school system dynamics modeling course I taught for 20 years at 2 different high schools, I do have copies of some of the student original models that they produced in this course on my website to verify that high school students are very capable of deep analysis of problems at their age. I have a link here that provides for you a copy of a linear model lesson that you could use as a first lesson in your class if you are interested. I wrote 2 books of lessons, both published by IC Systems. The first contains most of the lessons I have used in my algebra, pre-calculus, and calculus classes. The second contains the lessons I used in my system dynamics modeling course. These books are written so a teacher only has to purchase 1 book. The book contains the teacher's answer key for the student lessons. The student lessons with empty boxes to hold their answers and the completed models that go with the book can be downloaded and used forever. These books are available in both e-book format and paperbook format. I offer 3 online sequential system dynamics modeling courses each summer for teachers interested in learning system dynamics. Each is a 10-week course, is asynchronous, and contains about 25 instructional videos. It provides a gentle introduction to system dynamics modeling, and it has lots of models and lessons that can be downloaded. Each has been updated with some suggestions for using artificial intelligence, actually free large language models, in system dynamics lesson construction, creating systems thinking system dynamics assessment questions, and in the second and third course, building small system dynamics models from text descriptions. This is an email you can use to reach me. If you are interested in these resources, you may want to do a screen capture of this slide. Thank you.
All right, is now on to the questions and answers. We don't have any yet, so we'll be waiting for those. But while we are waiting, I have a question. Diana, did you ever find that certain projects clicked faster with students?
I think, well, the students loved the medicine models because it was part of their experience. All of them have had to take aspirin at some point in time, and whether we like it or not, quite a few students are exposed to the alcohol consumption scenarios. If the models relate to something that directly affects them, or if the models relate to something that they are learning in other classes, as long as the models are not too complicated, and especially if the models reinforce what's going on that they're supposed to learn as a regular part of the curriculum, I found the students to be very interested. I also found that my students who were not very good traditionally in mathematics, that they really liked another way to represent or mathematize the problems. It made more sense to them, and there was an increase in participation on their part. And I liked that a lot too. Did I answer your question?
You did, thank you.
Okay.
All right, we have a question as I would like to teach limits of models to teach. I would also like to teach limits of models to teach the risk of technocracy. Do you have developed cases for that?
I don't, but it's going to become more and more an issue as artificial intelligence becomes part of the modeling process. And I think it's going to have to be developing a best practice approach to the use of technology. I think of it with the application of artificial intelligence, which is at the top of my mind right now, and with the my colleagues that I am working with to try to address how teaching is going to be different with that fast-moving technology, is that we have to consider the artificial intelligence as like a smart but kind of crazy colleague. It can help you do things sometimes in a different way or a little faster, but sometimes what it gives you is not even reasonable. So I think it's important for students to develop a really critical eye when they are using technology. Even with calculators, we had to worry about students typing something into the calculator and spouting off the answer as if, well, it was in the calculator, so it had to be true, without analyzing whether or not what the technology gave them was even a practical response to the question. So yes, we are going to have to be much more diligent about having our students be critical of new technology, and that's going to be much more important with the use of artificial intelligence in our classes, because kids are going to use it whether we intend them to or not. Did I answer your question?
I believe so.
Okay, I hope so.
They'll respond if they have more information.
Okay.
But we do have another one. Can you speak a little about resistance and support you got from administrators and colleagues that may have been more closely tied to a content coverage?
Okay. So, my administrators were very supportive in both the schools that I used this particular approach in. Part of it, I think, came from the fact, well, I tried to talk to my administrators when I started with this so they would understand what I am doing in my classroom. I even did some presentations to my administrators in my first school because this was so new to them, to show them why I'm doing this in my class and how powerful it can be. I often had administrators who did not have strong background in mathematics, and they were especially pleased with the additional access to the problem that the modeling provided. Moreover, my students performed well on tests, state tests and national tests. So they were not giving me a lot of pressure to do something different because the student performance was not suffering because I brought this in. And every single time I had a chance to talk to parents, I explained this to them. I never, over 20 years, had one parent complain to me that I was doing this in the classroom. I had many parents say to me, I wish I had learned this when I was in school. So the reaction was from the students and from the parents and from the administration was always very positive. The resistance that I have felt both during and after getting out of high school teaching, retiring, was from other teachers who were nervous about the possibility that they didn't know how to do this and they were unsure about how to use it. And so I think it's really important not to force teachers to use this approach, but to invite teachers who are interested in trying something different in their classes, trying to bring in students who are not well served by traditional math classes, to invite them to learn how they can learn this approach, which is the reason I built my courses, my online courses, in a gradual approach rather than a compressed, fast approach that was typically of what I had to study when I was learning about system dynamics. And having my courses relate to what they already see in their courses so they can connect the new information to what they're already doing. It's important to connect the system dynamics to the current curriculum so teachers see that this is a way to enhance their instruction of what they are already being expected to teach, in addition to which they get all the value of bringing in richer problems to their classroom that are more interesting to the students. That's a long answer, but I feel pretty strongly about it, and I have not had resistance from the people that are really important to me, my students, the parents of my students, my administrators. I just need to figure out better ways to help my colleagues be willing to take the leap to learn this, but by invitation only. That's the only way it's going to work with teachers.
Great. We don't have any more questions right now, so thank you all for joining us for our 6th presentation. This is a recorded video, so you will get a copy of it in about a week. And again, thank you for joining us.
Thank you all for coming. I'm happy to talk to any of you individually, so just email me and I will respond. Thank you.